Hello everyone, I am going to explain you about a one topic on double-ended clipper, which is also called as dual or combinational clipper. So if we want to clip the positive end and negative end, or positive peak or negative peak, here we will use a double-ended clipper. So to clip the two ends, here we are using two diodes which are in parallel to this circuit. So this is the basic circuit diagram. In this circuit diagram, we are using one source resistance and the two diodes D1 and D2, and we are connecting D1, which is in a forward bias direction with the reference voltage plus VB1, and D2 is a reverse bias direction with the reference voltage minus VB2. This is the resultant output of your double-ended clipper. This is your input signal with the reference voltage plus VB1 minus VB2. I want to clip the positive peak above the reference level and negative peak below the reference level. So this is the resultant of your double-ended clipper. So this is a clipped portion of positive peak, negative peak. Now we will see this basic operation. So what are the requirements? Means it consists of the input signal, which is Vi is equal to Vm sin omega t, and the diode D1 is forward bias with the reference voltage or biasing voltage is plus VB1, and the D2 we got D2 is connected in reverse bias direction with the reference voltage biasing voltage minus VB2. So coming to the working operation. So here for in detail operation, we are taking an input signal with the two cases, that is during positive half cycle as well as during negative half cycle. So here we are using two reference levels VB1, VB2. So therefore here I am taking the positive half cycle in two ways, like positive half cycle Vi, which is greater than VB1 condition, and another one is less than VB1 condition. Similarly, during negative half cycle, the input voltage is greater than its cut-in bias voltage minus VB2, and input voltage less than minus VB2. So from these two, positive half cycle, negative half cycle, we are going to take the Va greater than VB1 condition and Va less than VB1, and Va greater than minus VB2, Va less than minus VB2. So from these two conditions, I am writing one common condition that we will see here. So this is the input signal, which is Vi is equal to Vm sin omega t. So here I am considering during positive half cycle. Let us assume it is T1 time period, that is T2. So in the time period 0 to T1, we already just now discussed, we have two conditions, Va greater than VB1, Va less than VB1. So here this is my reference voltage VB1. So this is the input voltage and this is the reference voltage. This input voltage is greater than this reference voltage. So I am writing this condition as Vi greater than VB1 condition. Similarly, here I am taking the another reference voltage, which is minus VB2, and this is your input voltage. This input voltage is less than this VB2. So therefore I am taking this condition as Va less than minus VB2, and the region in between VB1 and VB2. In these two regions, the input signal is there. So I am here taking the condition. So here input voltage is less than the VB1 as well as greater than the minus VB2. So for this region, I am taking this in signal as VB1, which is less than Vi, which is less than minus VB2. Okay, so therefore from this one we are getting a one condition, VB1 which is less than the Vi voltage less than minus VB2. So from these four conditions we are taking the three conditions. One is Vi greater than VB1 condition and less than VB1, and which is less than minus VB2, and Vi less than minus VB2. So from these three conditions we are going to see the operation of the double-ended clipper. So this is the first case, Vi greater than VB1 reference voltage. So in this case, so applied input voltage is greater than the reference voltage. Then we know The diode D1 gets forward bias condition and acts as a short circuit. Similarly, the diode D2 gets reverse bias and acts as a open circuited. So the entire input is totally limited to your reference voltage VB1. Just see here we are taking the first condition VI greater than VB1. So if your applied input voltage, so positive signal is greater than this reference voltage, so therefore then the diode gets forward bias condition and acts as a short circuit. But whereas the D2 diode, here you are applying a positive peak signal which is much greater than your diode cut-in voltage. So here the D2 diode gets reverse bias condition, therefore it simply acts as a open circuited. So therefore if your applied input voltage much greater than your cut-in voltage, this diode gets forward bias and acts as a short. Otherwise it gets reverse bias condition. Okay. So as we just now see here, na, the entire input is limited to reference voltage. So here input voltage Vi is greater than VB1 condition. The diode D1 gets short circuited. So entire input is totally limited to plus VB1. Coming to the diode D2 gets open circuited. So therefore this VB1 output appears across your output. Therefore, so this is our input signal for this region is greater than VB1 condition. So in this region, the entire input is limited to reference voltage VB2. So VB1. So therefore, V0 is equal to VB1. So this is the first case. Coming to the second case, in the second case is VB1 less than the VI less than minus VB2. So in this case, the diode D1 gets reverse bias because your input voltage, so this is your input voltage, this input voltage is less than your reference voltage. So whenever your reference voltage input voltage is less than the reference voltage, means it simply the diode gets reverse bias, because if it is zero reference voltage, we are saying zero above positive, zero below negative. So if you are going to, like, this is an input signal, means zero below signal is negative, for negative diode gets reverse bias. Similarly, so here this is your reference voltage, reference above voltage is diode, consider it as positive, reference below is negative. So here what is your voltage here? Vi is less than the VB1. Whenever Vi less than the VB1, the diode D1 gets reverse bias and acts as a open circuited. Similarly, the diode D2 gets reverse bias and gets open circuited. So the entire input appears across your output. So this is your circuit diagram. The diode D1 gets reverse bias because your applied input voltage is less than the VB1 and greater than the minus VB2. But here the diode D2 is reverse bias. We connected in reverse bias condition. So with respect to that minus VB2, it is a positive voltage. So the diode gets reverse bias and acts as a open circuit. So the entire input totally appears across your output. So this is the region. This is less than VB1, greater than minus VB2. So what is here V0? V0, whatever your input, either as input goes down to 0, 0 to minus VB2. So output follows it. So V0 is equal to VI. So in this region, see here, so output is equal to input. V0 is equal to VI. Similarly, in the third case, VI is less than minus VB2. So this is the region VI less than minus VB2 condition, means your applied voltage is much less than your input voltage. Your applied voltage is much less than your reference voltage. So therefore, for this negative voltage, reverse bias diode acts as a forward bias. Coming to the D1 diode acts as a reverse bias because it is a much negative voltage. So for this negative voltage, this is a forward bias diode. So it acts as a open circuited, whereas D2 diode acts as a short circuited. So in this case, your entire input, like much less than input, appears across your D2, because this D2 is got short circuited, and whatever the negative, much negative voltage, entirely limited to minus VB2. So see here. So this entire input voltage limited to minus VB2. So hence V0 is equal to minus VB2. So this is the entire output input output diagram. So here I am making the input as a dotted ones, output with a red one. Okay. So therefore, for greater than, we consider three regions. VI greater than VB1 condition. So therefore, in this condition, we got the output is V0 is equal to VB1. Positive peak entirely limited to VB1, and in between region. So whatever here, this is the region less than VB1, greater than VB2. In this region, we have got V0 is equal to VA. What as the input goes down, output follows it. As the input goes up, output follows it. And coming to the third condition, V0 is equal to VB2 minus VB2. So in this third condition, entire input is limited to minus VB2. Therefore, it looks like a, if the frequency changes, this waveform looks like a square wave. So as a sine wave is given, we are getting the output as square wave. This is also called as sine to square converter. So it has a double-ended clipper, a dual clipper, or combinational clipper, or sine to wave clipper. So this is the operation of a double-ended clipper. Double ends are, two ends are got clipped off. Thank you.